In this supplemental video, we are going to talk about the concept of electronegativity and its impact on the way that some molecules will interact with each other and with other molecules. So electronegativity is the ability of an atom to attract electrons to itself when in a chemical bond. And that's the key important part there. It has to be within a bond. We're not talking about electrons being drawn to an atom that's by itself. We're talking about electrons being drawn to a bond. And what we see is that when we have those two atoms in a given bond, they can share electrons in different kinds of ways. They can share them evenly. Um, and when they do, we call that a nonpolar bond. They can also share with each other unevenly. And depending upon how unevenly they share, they can either result in a polar covalent bond where they're still sharing electrons with each other, but electrons are spending more time with one of the atoms and less time with the other atom. Or we can talk about ionic character in general, where the electronegativity difference is so great that the electron literally leaves the one atom and goes to the other. And the way that we can measure this, the way that we can predict this kind of behavior is based upon electronegativity, and more importantly, on electronegativity difference. That is, the difference in the electronegativities of one element versus another. The bigger that difference is, the more ionic the interaction between them is going to be. So from that standpoint, let's explore this concept a little bit further. Where we get the values are from something called the Pauling electronegativity scale. The electronegativity scale tells us which which elements are going to have a greater influence on the electrons in the bond versus others. And the one part of the bond that has the more electronegative element, that draws the electrons more toward itself, we say that that particular side is partially negative. And we give that partial negativity a sign. And it's this goofy looking D. This is actually the lowercase Greek letter delta with a negative charge on it. The side that has the lower electronegativity, that is less interested in the electrons in that bond, that gets a delta positive, a partial positive sign. And so what this creates is, if we have a bond that is being introduced, then what we will see is that the side that is more electronegative is going to end up having a partially negative charge, and the side that's a little more electropositive, that has a lower electronegativity, is going to have a slightly positive charge on it. So this here is the Pauling electronegativity scale, and we can see that, generally speaking, as we go toward fluorine, so as we go to the right and up, our electronegativities tend to increase the most. And fluorine, with an electronegativity value of 4.0, has the highest electronegativity of them all. And this is important to us because what this tells us is that any atom, any element that is bonded to fluorine, is going to be pushing its electrons toward that fluorine. That's how electronegative it is. The more electronegative that a substance is, or that an element is, the more that electrons are going to be attracted toward it when it's in a bond of some kind. But we can see overall the trend is pointing toward fluorine. So nonmetals tend to be more electronegative than metals. That shouldn't be surprising to anybody. But within the nonmetals, we see that on the whole, nitrogen, oxygen, fluorine, chlorine, bromine, those tend to be the most electronegative. Those tend to have the greatest attraction to electrons overall. So what does this tend to mean? If we're comparing a polar bond where we have this electronegativity difference versus a nonpolar bond where all the electrons are being shared very evenly. What we can say is that polar covalent bonds tend to be shorter and they tend to be stronger because overall they've got more ionic tendencies, and ionic bonds tend to be more strong than covalent bonds are. By contrast, nonpolar bonds tend to be longer, they tend to be weaker as a result. When we start to apply the concept of polar bonds to molecules, what we get are polarity in the molecular sense, where the whole molecule has partial negative and partial positive charge. And this is driven by, I have to have polar bonds. And if I have polar bonds, then I need to have those polar bonds arranged in such a way that I can get a negative side and a positive side. And so molecular polarity tends to give us some very unique properties in molecules in terms of the kinds of things that they dissolve in, the kinds of boiling point temperatures that they have, and so on. So how do we identify polar bonds? Well, again, we have to use electronegativity, and in particular, we have to use electronegativity difference. The greater the difference between them, the more polar the bond is. And so what we're looking for here in general are just kind of generic trends. If our electronegativity difference is 0 or really, really close to 0, 0.1, 0.2, we're not going to make too much of a deal about the polarity of the bond itself. We generally are going to consider those bonds to be nonpolar, and as a result, the molecules that they create nonpolar as well. Anything above that is going to exhibit some level of polarity. But if we get to an electronegativity difference of 2 or more, then we start going from, is this really a sharing of electrons? Is this really a covalent compound? Or are we delving into the ionic territory a little bit more? And so, as a general rule of thumb, we talk about any electronegativity difference greater than 2 as being pretty much going and crossing that line and going from covalent to ionic. So if we see electronegativity differences greater than 2, we tend to think of those compounds as ionic compounds instead of covalent compounds. So the question is this. I've got 5 molecules here. Which of these molecules have polar bonds? And of the polar bonds, which ones are the most polar? So the way to do this is to look at the electronegativity scale. And so what I've got in sulfur dioxide is I have a sulfur to oxygen bond. What I need to look for is what is the electronegativity of sulfur and what is the electronegativity of oxygen. So I go to my scale, I see that sulfur's electronegativity is 2.6, oxygen is 3.4. Our difference there is 3.4 minus 2.6, which is 0.8. So we're talking about a polar bond, but it's kind of in the middle. It's definitely not nonpolar, but it's definitely not ionic. Let's see how that stacks up. For nitrogen, we're talking about nitrogen to nitrogen bonds here. This is actually a triple bond, not that that matters for this particular activity, but I go to the Pauling scale here and I see that nitrogen has a electronegativity of 3.0, and the other nitrogen would also have an electronegativity of 3.0. The difference here is 0, so this is a nonpolar substance. These are nonpolar bonds. And as a result, the substance itself, nitrogen, is a nonpolar molecule. You can't have polar molecules if you have nonpolar bonds. Third example, we've got H2S. So we're going with our H and our S bond. The hydrogen has an electronegativity of 2.2. The sulfur has an electronegativity of 2.6. Our difference here, 2.6 versus 2.2, is equal to 0.4. So again, we're dealing with polarity here, but we can see that the difference here, our polarity is considerably less in the H2S compared to the SO2. So right now, SO2 is still the most polar. Our last ones here, let's see, we've got carbon tetrachloride. So we've got a C to Cl bond. And so go to our table. Let's see, carbon is 2.6, chlorine is 3.2. So our difference there, 3.2 minus 2.6 is 0.6. So again, polarity, definitely more polar than the H2S, but not nearly as polar as the SO2. The last one, we're dealing with ozone. Ozone has oxygen to oxygen bonds. We already got the electronegativity from the SO2 example. It's 3.4. So here our difference is equal to 0. We're dealing with a nonpolar bond here. So of the three molecules, we can evaluate that this one's polar, this one's polar, and this one's polar. Of the three, the bonds in SO2 are the most polar, given that they have the largest electronegativity difference. So that's all that you really would have to do in that realm, is take those electronegativities off of that table, compare them to each other, and whichever one comes out the biggest, that's going to be the most polar. And again, so long as the values are greater than 0.1, 0.2, we can consider it to be polar. Short of that, we start to really kind of question how polar it actually is. Now, why does this matter? Where does this come into play? Well, polarity has a lot to do with solubility. With solubility, we like to use a principle called like dissolves like. And what that means is that substances with similar polarities are going to dissolve in each other, and ones with opposite polarities are going to tend to repel each other. So if I have something that is a polar molecule, it is going to dissolve in other polar molecules. If I have something that is a nonpolar molecule, it's going to tend to dissolve in other nonpolar molecules. And generally speaking, polar molecules and nonpolar molecules do not mix with each other. Instead, what we'll get is stuff more along this line, where we see that they layer up on each other. They just completely separate from each other. In this case, we've got oil and water. Probably the most classic example of polar water versus nonpolar oil. And so that concludes for us this supplemental lecture. This closes out for us chapter 8. Just wanted to kind of give you a little bit of that insight here before we completely close the book on it, because there were some things that you might see and you might just want to be aware of as you're doing the homework assignments and things. So that's all for now. I will see you next time. Have a good weekend.